All right, welcome everyone to the class meeting for week 4. Can't believe we're already in week 4 and 12 more to go. I don't want to think about that. I had to wear my hat today because I just look gross today, but you know, it's week 100 of COVID-19 or wherever we are, I don't know. All right, so I'm just gonna have you guys do your own opening prayer because these girls that are always here, they're gonna be praying every week, so I'm just not gonna make them do that. So please go ahead and have your own opening prayer with yourself to invite the Spirit, because it's hard for me to teach if the Spirit isn't with you. So it's totally all about having the Spirit. So let's go into week 4 then. Oh, let's see, what was I going to say about 3? So oh my goodness, sorry about that. So your essays are good. I made comments on group 1 and group 3, and Ashley's going to finish making comments on group 2 discussion boards. And then, so make sure that this week you go back and comment on if you haven't participated in the discussion board yet. And if you have, go back and check yours by Thursday, your post, and make sure that you reply to one or all of the comments that have been left for you. A lot of times you just go in and you answer them, and then we get a whole big long thread of discussion, which is what we want. But remember to be parsimonious. I love big words. With your comments, go to people that don't have any, and don't just stay on the same one. Try to find other people that haven't had an opportunity to discuss anything with anyone. So share the wealth. Okay, I think that's all. Oh no, let's talk about the bugs. So I forgot that the bugs were this week, weren't they? Did we have to figure out what the bugs were doing? So you put them on the pen. The guy drew the circle with the pen, and the bugs went around the circle. And then he did it with another color. He did it with like 3 colors on with the same pen. Then he used the marker, and he did the indentation, and he flipped the page over. And hey, some of them just couldn't find the circle, and they just kind of went everywhere. So anybody that's here, so Annalisa or Gabby or Carolina, anybody want to volunteer what they think was how the termites were able to do what they did? Any ideas? Gabby?
Well, after watching all of them, I at first thought that it was sight, because I did notice that the blue and the black ink were a little darker. So I just assumed that maybe the pink and the green and the highlighter, they just were not as dark. And then the indentation ones, I thought, okay, so it's not the sense of touch, and it wasn't. Anyways, I thought it was sight, but then after retaking it, I was like, wait a minute, is that what it was? And I did think about it, and I was like, well, you know what? Whenever you're writing, like in blue or black ink, it does have a stronger scent.
It does.
And I just kind of thought of that on my own after retaking it, but I would have thought it would have been their vision.
Exactly. And that's usually what my students pick. And the reason why we wanted you to do that activity is so that you could see, oh, I was wrong, but that's okay. So let me go back, make some more observations, figure out some more things. So the first thing is that termites are blind. And so, yeah, that would have been nice to know, but no, you didn't need to know that. It was good to figure out the way that you did figure it out. But yeah, termites are blind. So they do go by scent, but like Gabby said, a particular scent, not just any scent. So when he did the blue and the black, he did it with the same pen, and then he did the other pens that didn't have that same scent. So whatever was in that ink that attracted them, that they wanted to go around in a circle, then they follow that. And then they also have their own scent. And so when at the very end you had one that went around in the circle, and then you had others that go around too. So a lot of insects leave pheromone signals behind. I shouldn't call them pheromones. Scent trails, because pheromones are different. They are chemical signals, but typically pheromones are used to attract a mate. And so humans don't have pheromones, in case you heard that before. No, we have scents, but that are significant others are attracted to, but they're not classified as pheromones. Pheromones are pretty crazy. You can take a yucca moth. I just know these weird things. So a male yucca moth can smell a female yucca moth up to a mile away. So that scent can just waft, and he can find her, and they can have yucca moth babies. So anyway, okay, so that was about it. Yeah, that's all we're going to talk about now. So let's go ahead and go into week 4 and continue on knowing more about what science really is. Maybe. Okay, there we go. All right. Excuse me. All right. So how does science work? Is science like following a recipe in a cookbook? That's probably the experience that you've had in your previous science experience in maybe high school or middle school. Yeah, you have the list of ingredients, you have the steps, and you should get a cake at the end. So yeah, it kind of is, but it kind of really isn't either. It's too simple for us to just ask the question, formulate a hypothesis, perform the experiment, collect data, draw conclusions. Boom. It doesn't go in that stepwise fashion. And I showed you last week the How Science Works flowchart, so we're gonna expand on that some more today. So we're going to see how is it more than this. But is there value to doing this? Were we really doing something for you when we were teaching you that way in high school? I used to teach. I taught high school for 15 years before I came to the college, and there is value in that, because when you're younger, you need to have things more organized so that when you are given just free reign, you already know what you should be doing, and then you can have a jumping off point. So they do oversimplify science, but like it says, can show that science is based on testing ideas and can be used to reinforce other investigations. And I'm going to refer back to that later on as we go through things tonight. All right, so in the on-campus classes, they have a little class activity. So this is just the slide from that class activity, but I'm going to actually do this with you. Well, it's part of the class meeting quiz anyway. Well, the second part is, but I'm going to show you how to do number 1, and obviously you don't need to do it yourself, but we're going to use the process of science flowchart to walk through the process of dating from beginning to end. And we want to make sure that we use as many little bubbles as possible and not just the big giant bubbles. So let's go to this, and let me get a pen. And I don't want to do it in that color. Let me find a good color. We'll do it, and this will really show up. Okay, so dating at BYU. So yeah, I dated at BYU. I went to BYU Provo for 6 years. I got my bachelor's degree there, and I got my master's degree there as well. But yet I did not get an MRS degree while I was at BYU, and really disappointed. Really had hoped that I would, and that's fine. I found someone somewhere else and had 3 incredible, wonderful children that I adore with all of my heart. And so it was fine. But I always feel like if you get out of BYU, either BYU I do or BYU Provo, if you went with the intent of getting married and you got a degree without getting married, they should refund at least part of your tuition. Probably not all of it, because then I couldn't get a salary, but no, I'm just kidding. But I was bummed for a long time that all I got from BYU was a degree. All right, so I had a practical problem. I wanted to get married. I wanted to get married and have babies so badly, okay? I also had some personal motivation. All right, so I can come at my exploration and discovery of dating at BYU in the 80s, um, either as a practical problem or personal motivation. So what do? Well, I need to make observations. And the time that I was there, I made a bunch of observations. I went lots of places and I looked for lots and lots of boys. And boys that I met in my classes or that I saw down at the Smithfield house when I was working out or something like that. And so once I made those observations about, ooh, that boy looks like somebody that I would be interested in dating, then I need to ask some questions. Ask my friends, ask other people in the class. Do you know if he's married? He doesn't have a ring on his finger. Where's he from? What's his major? All that kind of stuff. Or I could ask those questions of him. And then my friends could say, okay, well, here's what I think you should do about meeting him. Okay, so we've observed these kinds of things about him. I guess I should circle my bubbles. We've observed these things, and so we think this would be good. Hey, look at that, finding inspiration. Even University of California, Berkeley thinks that we need inspiration. And I don't know how many times I prayed about finding somebody. Not a lot of literature on a particular boy, but there is literature about how do you go about, asking somebody out or something like that. And remember, girls and boys, I'm sorry, it's just because there's girls in my class right now, in my Zoom meeting right now, but I forgot what I was going to say. Oh yeah, that was the 80s. So you didn't really ask, girls didn't really ask boys out unless it was like a girls' choice dance, like a Heritage Halls Invitational or something like that. Heritage Halls isn't even there anymore, but at least the ones I lived in. So anyway, so I practical problem, made some observations, I asked some questions, got some data and some ideas. I prayed about it. I read some information about how not to be shy. I don't even know. Okay, and so then I find a boy, several boys at a time, or from time to time, not at a time, but from time to time, and I thought, okay, I think that he really likes chocolate chip cookies. So I'm going to make him some chocolate chip cookies. So there's my hypothesis. If I show him that I'm a really good cook and I make really good chocolate chip cookies, at least maybe he'll be interested in going out with me. Okay, he might ask me out. So that was my expected observation, was that he would ask me out. So I take in the cookies, and what kind of conclusion did I make? How did I interpret my data? Well, it could be supportive, could support my hypothesis in that, yeah, he did like my cookies and he did ask me out after that. Or it could be contradictory. Maybe he was gluten-free. And so then I needed to come up with some other way to inspire him to ask me out, or that I should have assumed that he was gluten-free and tried something else, or he's just not interested. So where do I go from there? Well, and I go back up here, and then I do this all over again. Then I come down through here and I find out another hypothesis and what I expect and actually observed, and what are my supportive, contradictory, surprising, or inclusive or inconclusive data. And then I go, okay, well, he asked me out or not asked me out. What should I do now? Well, then I come over here and I need the girl community to help me out with this discussion with my colleagues or maybe other guys. What am I doing wrong? Okay. And then they give me feedback and peer review what I'm doing. And maybe they show me how what I'm doing is wrong. And I'm not going to I write it in my journal, I guess. I'm going to try that again. And then come up with new ideas and questions, which then can lead me back to my exploration and discovery, and then try it all over again, or just back into my testing. Or then maybe after they tell me, then maybe it helped me solve an everyday problem or satisfy my curiosity or build my knowledge, or something worked and I came over here and here's my problem of I didn't have a husband and now I do. And so then I can come back up in here and come to a new problem. So you can use this not with dating. And I'm just going to do one more thing because the class meeting questions specifically about dating. But here, for those of you who are not dating or don't care about that kind of thing, here's probably my favorite one of all is, here's my practical problem. Where the heck did I leave my keys? Okay, they're not where I found them. I go to my kids. Kids, where are my keys? I don't know where they are. I pray about it. Where are my keys? I don't know where my dang keys are. Ask my kids again. Where are they? So, well, Mom, I think they were on the kitchen table last time I saw it. Okay, kitchen table. I expect to find my keys on the kitchen table because my kids are not lying to me. I actually find out that no, they are not on the kitchen table. So now what do I have to do? Well, I have to go back up in here and I have to make some more observations. Well, okay, so let's try. We got some more data, and I pray about it some more and I get that feeling like, oh, they're under the carpet. So I go over here and they're under the carpet and I expect to see them under the carpet. And then when I get down here, found a lot of other things under the carpet, but not my keys. So I gotta maybe find some other help or whatever, and then come back up in here. And so even just everyday kinds of problems, you guys, we use this all the time. And we learn from a very early age to do the trial and error kind of thing. And we go through all of these steps without even realizing. We go through all of these steps all the time. It's just that University of California, Berkeley put this in a nice little bubble thing, nice graphic, so that we can realize, oh, okay, here's what we're doing all the time. Okay. All right. So there's my life in a nutshell. Okay. It's my romantic life. All right, so exploration and discovery is the very first one. So let's go into what does that entail. So this is where we get started, and we need a place to get started. So we either need maybe some new technology, or we have a practical problem, or maybe we're just curious. We're going to look at some of this curiosity aspect and surprising observation and serendipity as we go through the rest of the semester. We're not going to just leave, look at this once and then leave it. We're planning on revisiting this often. Personal motivation. And so once we've done those things, once we have these things that drive our exploration and discovery, what do we do? So what do we know what to test? We must first make observations in the natural world, and then we develop a question and hypothesis. So here we are making observations. I'm just curious about, does this cute boy like kitties? I don't know, something stupid. But so then I look to see if he's ever around cats and whatever. And so once I make observations, and maybe I'm a real cat person, then I need to test that. But I make some observations ahead of time and I ask some questions. And then we develop a hypothesis, and that leads us. So scientific inquiry is helping us know, what are we going to test? Not how we're going to test it, but what are we even testing in the first place? So we make observations, and then we make our question and our hypothesis. And so then that's going to take us to the testing ideas portion of the chart, where we take our hypothesis, when we gather data. Now, the most important thing you guys need to understand for the whole rest of the semester is that when we form a hypothesis, we also have expectations. We also expect something to happen. So we don't go in with a hypothesis and have absolutely no idea what we're going to come up with. We have an expectation. We have the answer already. If I water my plant, I expect it to grow. There it is. So my question was, do plants need water? Or how much water do plants need? And so I think they need X amount of water. So I don't expect them to die when I water them. I expect them to grow. I just don't know how much they're going to grow. And so when my hypothesis is correct, then my actual observations reflect my expected observations. All right, now when we're testing, we need to realize that a single idea can be tested multiple ways. And so maybe if it doesn't work out the first way, then we can try another way. We shouldn't just toss our hypothesis in the garbage. Maybe it just needs a better method of testing. We can make some assumptions, and we'll go to assumptions in just a little bit. What is an assumption? It's not what you think it is. And then results must be compared back to the expected outcome. So the actual results, the actual data must reflect, or we make a comparison so we can say, oh yeah, it really did match my expected, or it didn't match my expected at all. But we have to have an expected so that we can see what do the actual data reveal. We need to make sure, and we'll talk more about this later, but we need to make sure we test only one variable at a time so they know if the variable produced the observed results. So let's go back to my tree when I water it. So I'm gonna water my tree, and I have another tree that I'm not gonna water, and if I want, or maybe I can just take my one tree and I'm gonna water it and I'm gonna see if it grows. Now, that means I can't change the dirt, I can't change the amount of sunlight, I can't change the temperature, I can't change the amount of wind it gets, I can't change daytime exposure, I can't change anything. The only thing I can change is the amount of water that I give it, so that I know, yes, for a fact, it was the increasing amount of water that I gave my plant contributed to its growth. Okay, so that's why we only test one variable at a time, so we know which caused the outcome. All right, now conclusions are super important, because we should always look at the conclusions to see if we need to refine, so make it, tweak it just a little bit better, or revise, or experiment further to collect more data for support of our hypothesis. Okay, now, which is more valuable, an idea that explains expected results or one that explains unexpected results? Okay, well, if we have an answer to a problem that just answers our variables that we produce with that thing that we're testing, sure, it goes ahead and answers that question. But what about if something else happens to the plant and it can't explain that as well? So it's always better that the answers that we have, or the hypotheses that we come up with, will explain unexpected results too. And when we get into talking about theories, that'll make more sense. Be able to explain things that we haven't seen yet. But not next week. Well, week 7 is when we'll really get into talking about how do you come up with something that that explains unexpected results. Okay, so what happens to our hypothesis? Well, 3 things can happen with our hypothesis. So we can get evidence that may lend support to one hypothesis over others. We can get evidence that may help rule out some hypotheses, or the evidence may lead to the revision of a hypothesis. Okay, so we end up getting one, or we may just rule out some of the others, or we may have to just throw out the hypothesis and come up with a new one. So those are the things that can happen with once we've tested that. Okay, so now we're going to take a look at what are assumptions. So let's go back to our plant, our tree that we're watering. Okay, I'm going to assume that the water, okay, no, let's go back. I'm going to assume that the pot that my tree is growing in I don't have to test to see if that pot has any effect to do with my tree, because lots of other people have used that pot to grow their trees in. It's just a place to put your plant, and it doesn't affect the outcome of your experiment. Or it doesn't need to be tested because so many other people tested it that we know that it's okay to do it a certain way. Okay, so why would we even care about that? Well, remember that we have to keep only one variable can change. Everything else needs to be kept the same. And so if somebody has already decided that, yeah, this is a good container to grow your germs in, like CDC's probably already got some assumptions with the coronavirus testing, the actual virus testing, so that it speeds up the experiment. So there are aspects of an experiment that are not directly tested. So why do scientists make assumptions? To simplify experiments, not having to test things I assume to be true, or that somebody else showed that doesn't affect it. Do I have to accept assumptions as true? No, I could test everything, but to do so would severely inhibit the progress of the main topic or the main variable that I'm trying to test. So assumptions are just things like, okay, I can use this much soil, I can use this pot, I can be in the sun, you know, those kinds of things, outside of testing my one variable. All right, and then the last thing about testing is something called uncertainty. So uncertainty doesn't mean we're not sure about the results. We're simply looking at how confident we are that something happened because of the reason we were testing and not by accident. So there's two reasons why things happen. It happened because you were watering it, or it happened because of something else. Okay, so now we need to see how confident are we that it was because of the water and not because of chance that the plant grew. And so statistical analysis, which we'll get into later in the semester, why do we do statistics? Why do we do data? Well, because it helps us with our degree of uncertainty. Can we say it was because of watering it, or do we have to say, I don't think it was because of the water, it was probably something else, it was just by chance that when you watered it, it grew? Okay, so that's what that is all about. All right, so benefits and outcomes. So why do we do science? We can do it to develop technology. We can do it to address societal issues, to build knowledge, to inform policy, to satisfy our curiosity, and to solve everyday problems. The real important thing in here is that we're not doing it just to make money. Now, the development of technology does often lead to a monetary value of our science, but that's not why we do it. So we behave scientifically so that we can develop an explanation of the phenomena we observe in the natural world. Remember, the first step in the behaving scientifically checklist was explains the natural world. And that's why we do science. We need to, why do things do what they do? Technology, marketing, production are all just offshoots of science. They are not the core of science. We don't do science just to apply for a patent. However, next week we will talk about science being done for those kinds of reasons. And is it good science? Is it bad science? Is it real science? Is it voodoo science? All right, so that's not why we do it. Although there are, you know, okay, we're going to learn about, there are some people out there who did things just because they want to make money. All right, so then the last aspect of the science flowchart is community analysis and feedback. Why is that important? Well, we looked at last week in behaving scientifically that we need to involve the community so that we can take bias out of our results, so that, you know, we're just like, well, I'm right, and so I'm going to make sure that I cook the data so that it makes me look right. So everybody will give me lots of money to keep experimenting. No, that's bad. And we'll talk about that next week too. So what we have to do is, oh, and then in the little, you know, to get into the science club, you had to, all patrons must subject their theories to peer review. So yeah, we let other people look at our work, and then they tell us things about it. One of the things that when our peers are looking at our work is that we want them to replicate our work. We don't want to keep things, you know, under wraps. We want to make sure that we let people do what we're doing, because then it validates us and it helps avoid error and those kind of things. So this is really important, and we're going to spend a week. One of our essays is going to be specifically on community analysis and feedback. And what are some of the benefits of it? Well, help us come up with new questions and new ideas, and help us build theories, which is specifically what we're going to look at in week 9, I think it is. All right, so but what if replication doesn't occur? Well, other scientists may not be as precise as you were, or you didn't really know why you got the data that you did, you didn't understand the principles behind it, or you just flat out made a mistake. Okay, so so what we're going to be looking at for the rest of the semester, eventually starting in week 7, is scientific theories. And so what is a theory? It is a well-supported explanation of a physical system. So we see something in nature, and it's not just one thing. It's a big overarching idea that has a lot of hypotheses that fit together to help explain either observed or yet to be observed observations. Detected data, whatever you want to say. So we have the theory of evolution, theory of plate tectonics, the atomic theory, and the Big Bang theory, which we're going to be doing this semester, but not dinosaur extinction. That's just a hypothesis. So why the difference? It explains one part of why things go extinct, but it's not the overall arching extinction theory, because we probably can't come up with an overarching theory as to why things go extinct. But we have hypotheses that can explain that. But yeah, plate tectonics, for example, we have all of the things with the plates moving, and all of the observations that we see with that all lead to the fact that we have our continent and the crust of the earth is broken up into pieces, and they move. And then we can put a whole bunch of things in with that. Okay, now, speed of science. So science often crawls along, like COVID-19. What a great example. Right now, I'm sorry that we're living this example, but we are. So here's how that works. Now, wouldn't it be nice if we could just, boom, pop out a vaccine right now, so we can all go outside and we can all do everything, and we can go to baseball games again, and we can go to the movies, and we can go shopping, and we don't have to worry about transmitting this virus from person to person. So why don't we have a vaccine? Well, because we have to be sure. We need to ensure that the information that is being collected by, I think the last thing I saw was almost 17,000 labs across the world are, what? Hang on. My daughter just texted me something weird. Okay, sorry. 17,000 labs. I'd stop and think, where was I going with that? Across the world are working on COVID-19. And so this is our community. And so as one little place learns, oh, JC. Okay. And so everybody's helping each other and checking each other's work, and so that it is safe and it is accurate. But how, right? Oh man, Heavenly Father, how prescient was that question right there? How many could have benefited if we had known sooner? Thousands of people could have benefited if we had known sooner. But could thousands have suffered more than what already have if the vaccine we put out there started killing people because we weren't sure of what we were doing? Man, you guys, that really, I've had this up here for, I don't know, 10 or 15 semesters. It's really kind of hit me funny tonight. Sorry. So there it is. That's why sometimes science is slow. Okay, so that is all. Oh, my daughter's asking me stuff. Okay, so that's all that's for this lesson. However, I want to give you something just to wrap up that's going to go into next week's information, because what we're going to do is start on claim analyses, and a claim analysis will let us teach us how to decide if something is really good or if it's not. So, you know, you always hear, especially on Facebook and, oh, well, okay, let's just stick with COVID-19. So, you know, people saying, oh, well, you know, if you take these particular oils or you eat this particular vegetable or whatever, it's going to cure your COVID-19. How do we know? How do we know that's true? How do we know that it's false? And so when given any amount of information about absolutely anything, and next week is with our whole situation, it's going to be very interesting how we can look at some of the things that are being said out there and do claim analyses on them. But this is one thing that we can use all the time whenever we're deciding, you know, somebody wants us to invest in something. Oh, you know, this will make lots of money because this is a really good way to grow your hair back or lose weight or, you know, whatever stuff that we want to do. So back in the 90s, before Carl Sagan passed away, Carl Sagan was an astronomer. And just somebody that I really enjoyed when I was growing up. And so if you know Neil deGrasse Tyson, Carl Sagan was the Neil deGrasse Tyson of my day. And so anyway, he wrote a book called The Demon Haunted World, Science is a Candle in the Dark. So meaning that how do we find things here? We just live in this world where we don't know where we're going. We don't know what we're doing. How can science help us through that? And so one of the chapters in the book is called The Fine Art of Baloney Detection. And so here are some things to help us, some advice to help us when confronted with those strange and magnificent claims. So he says the kit is brought out as a matter of course whenever new ideas are offered for consideration. If the new idea survives examination by the tools in our kit, we grant it warm, although tentative, acceptance. If you're so inclined, if you don't want to buy baloney, even when it's reassuring to do so, there are precautions that can be taken. There's a tried and true consumer tested method. All right, so what do we do? So here is his baloney detection kit. So first of all, whenever possible, there must be an independent confirmation of the facts. That's why we have 17,000 labs working on COVID-19 right now. Everybody needs to, well, not everybody, but we need to have independent confirmation that what one lab came up with is really true. The second one, encourage substantive debate on the evidence by knowledgeable proponents from all points of view. Okay, now that one's driving me crazy right now with COVID-19. Substantive debate on the evidence, that's what we want. But knowledgeable proponents, people, we got everybody. And the media, you know, they pick up every last thought and say, well, here's what somebody said today, and here's what somebody said tomorrow, and so on. And I'm like, oh, please, people, you know, like, okay, wear the mask, but don't wear the mask when you're not supposed to wear the mask, because we don't know if masks really work, and we don't know if maybe that's going to concentrate the virus and make you sicker than you might have been before. Okay, what do I do? So that's what's driving me crazy right now is we're just throwing crap. Oh, sorry. We're just throwing stuff out there. Ooh, I'm so sorry about that. Just everything. And, you know, whatever sticks to the wall is the news media will pick that up. Okay. Number 3, arguments from authority carry little weight. Authorities have made mistakes in the past. They will do so again in the future. Perhaps a better way to say it is that in science, there are no authorities. At most, there are experts. And so people are going, oh, well, so-and-so is an authority on this, right? No one is, okay? So we have people who have good ideas, but the experts are typically the people that are going to say, hang on, let's look at this objectively instead of just, you know, standing in front of the camera and going, well, this is what's going to happen. Okay. All right. Number 4, oh my goodness, this is so pertinent today. Number 4, spin more than one hypothesis. If there's something to be explained, think of all the different ways in which it could be explained. How many things have you heard about how COVID-19 got caused? And I do not want any conspiracy theories, you know, bats or whatever. I don't know. Okay. So, and and how many of you have seen like the first, California. So patient 0 in California actually got sick back in February. And before we had even thought that it had come to the state, and had been to Italy and had been on a ski trip, and they discovered, oh my goodness, we got people being sick with this earlier than we thought was it actually, coming to America and stuff like that. So spin more than one hypothesis. Think of all the ways it could be explained. Think of tests by which you might systematically disprove each one of the alternatives. What survives the hypothesis that resists disproof is in this Darwinian selection among multiple working hypotheses. Has a much better chance of being the right answer than if you simply run with the first idea that caught your fancy. And what has that done for us? Okay, not a lot, because other things keep cropping up, and we have to go, oh yeah, well, our first idea was wrong, so come up with a bunch of them at the same time, and then you don't have to lose time by finding out that first one was wrong, and now we gotta go to another one. Try not to get overly attached to a hypothesis just because it's yours. It's only a way station in the pursuit of knowledge. Ask yourself why you like the idea. Compare it fairly with the alternative. See if you can find reasons for rejecting it. If you don't, others will. Oh my goodness, you guys, this is so pertinent today. All right. Number 6, quantify. If whatever it is you're explaining has some measure, some numerical quantity attached to it, you'll be much better able to discriminate among competing hypotheses. Okay, you can't just say masks work. Why do masks work? We need to see some numbers. How much does that reduce the amount of transmission? If it's not doing it at all, if we don't have any actual empirical concrete data, then why wear the mask in the first place? You've got to show the data. You've got to quantify. You can't just say, well, I think. Well, you know what? I think too. So what is vague and qualitative is open to many explanations. Of course, there are truths to be sought in many qualitative issues we're obliged to confront, but finding them is more challenging. And then if there's a chain of argument, every link in the chain must work, including the premise, not just most of them. So we have to say, yes, if you do this and this and this and this, we can flatten the curve in COVID-19. But there has to be a complete chain of getting from what I think to what I want or what I expect. And if there isn't a solid link in everyone, then you got to come up with something else. Okay, Occam's razor. This convenient rule of thumb urges us, when faced with two hypotheses that explain the data equally well, choose the simpler one. Why would something more difficult work better than the simple one? If the simple one works the best, that's the one that works. Think about Heavenly Father. Heavenly Father is a God of order. He's not going to go, oh, okay, we got to make sure all of these lines of evidence work. No, he's going to go for the simplest one possible. And that's Occam's razor. Okay. And then lastly, always ask whether the hypothesis can be, at least in principle, falsified. Propositions that are untestable and falsifiable are not worth much. Consider the grand idea that our universe and everything in it is just an elementary particle, an electron, say, in a much bigger cosmos. Okay, is that it? Have you ever thought about that? Am I just living on the bottom of somebody's shoe and that's my world, right? Okay, so I don't know. That's not really true, okay? But if we can never acquire information from outside of our universe, is not the ideal incapable of disproof? You must be able to check assertions out. Inveterate skeptics must be given the chance to follow your reasoning, to duplicate your experiments and see if they get the same results. All right, I'm telling you, friends, I have not used this better than the whole COVID-19 thing. And so as you're evaluating information that comes from, media about COVID-19, apply these 9 steps and see what that does for you. Does it help you make your decisions better about what's going on with this thing? Oh my heavens, you guys. Crazy, Who'da thunk it? Okay, so that is all that I have for today. And make sure you go through, I had to stop and think what this lesson was about. I got so excited about the baloney detection kit. The steps of the science flowchart, and then all of that information that I gave you about science at the beginning is all what the quiz is about, and then the study quizzes, the first and second study quizzes, and then the lesson meeting quiz is about oh my goodness, what did I just forget? Oh, dating and this flow chart. Okay, all right. So so that's all I have for today. Does anybody have any comments or anything that they want to ask me before we leave? Okay, no. Then have a great week, and make sure that you're commenting on people's things and responding. That's the most important thing, because you can only get half the points for the discussion board if you only comment and you don't respond. So make sure that you're doing that this week. Otherwise, have a great week. Our state just got opened up for a whole bunch of things today, or starting tomorrow. So I don't even know, that just came out on my phone. So I hope things are going good for wherever you are too in the world, and stay healthy and have a great week. We'll see you next week. Bye.
Thank you. Bye-bye.
You're welcome.